We don't need Sam. Let's get going. So I said we weren't going to do unit commitment, but you should know what it is. And also, there's a whole bunch of, today is like trash cleaning. So there's a bunch of things that I've alluded to and didn't make precise. And I've mentioned unit commitment a lot of times. I think I've made that precise. But you need to know something about it. So this is all of chapter 4 and more in one lecture, because it's just the details. I'll tell you where to go for that if you really want to learn this. So recap, which is a long recap and a little bit of lots of stuff to fill in, and what the unit commitment problem is, how people used to solve it, and how it's solved today. And so, remember last time this plot of onion prices in India. I love that. It's really real. I mean, there's riots in the streets when onion prices go up. It's either the housewives or the farmers that are screaming. And so we saw, some theory to explain why you'd expect crazy prices, and this was a bit, all of this is from my own work with this economist In Koo Cho, and that underlined there is a link you can go to if you want to see more. There's a book chapter on this. But there's no accepted explanation to the crazy prices. I mean, I can give this to a lecture to one set of economists, and they'll say, of course we knew that all along. And I'll say, give me a reference, Frank Wallach at Stanford. He and I have had a debate for my God, for 10 years. So there was an article in SIAM is a Society for Industrial and Applied Mathematics, and they, in 2005, they published a story about this article. It took 5 years for this to get published. And Frank Wallach wrote a counter to our paper, basically saying, this is known but wrong anyway. And it's been 10 years, and he's never given me a reference. So anyway, so you'll go, and some economists will say, well, we all knew that, it's obvious, and some will say, that's absurd. And they'll say negative prices can't exist, even though they happen every day. So there's no theory, there's nothing out there. So I can give you some mathematics that can give you one perspective, and with different assumptions, I'll give you different answers. And how does the world really work? How do people optimize? You'd have to get in the heads of people, and we can't. That's the trouble. And again, that's the difference between control and economics. In control, you watch the behavior of the airplane, and you change your decisions based on what you observe. That real-time closing the loop doesn't happen in other fields. It doesn't happen in economics. It didn't happen in communications until recently. There was no feedback. That's why communications required much more careful modeling than control, because of that lack of feedback. Okay, but this amazing result that average price is average marginal cost, and the outcome is efficient, even though the prices are going to $20,000 and minus $1,000. It's efficient in the economic sense. That's what's hilarious. And we looked at this problem. Okay. Now, again, what was missing? So what we did include was supply equals demand. We had ramp constraints, upper and lower limits of generation, and you all listed some other things. There's among the gaps are how many generators are we talking about? And what's that called, this decision? Unit commitment. And what is demand? That's a huge gap. What the hell are we talking about? Like, if this is day ahead, we don't know the demand. Just like we didn't know the prices, we don't know the demand. So there's huge gaps right there. So we're going to fill in this in 15 minutes today, and this is going to take us a few weeks. So in terms of unit commitment, I'm not really going to do this. This is mainly scribbles, but let's go and talk about some gaps first. So again, so at 4 p.m. today, we don't know supply or demand tomorrow.
I don't think we went over unit commitment at all.
No, this is today. So that was recap.
I don't even think we went over that either.
Yeah, we did. Oh yeah, we did. We solved we had ramp constraints, and we proved that average cost was average marginal price. All that lovely stuff. Yeah.
Use that equation again.
Well, we did, actually.
Well, yeah.
Yeah, that was a social planner's problem, basically. We wanted to minimize this subject of supply equals demand. You know? Yeah. Or this would be the, yeah, okay. So we did all that, and we have discussed gaps, yeah. So, but, and I'm going to come back to this a little bit, but in terms of unit commitment, this is the kind of thing that you'll see. This is old, by the way. This plot is from 2010. You know, and you've got their day-ahead demand forecast and the actual demand. And you see a bit of a gap. It's quite large, really, because I mean that scales in gigawatts. So the area there is maybe 400 megawatts. That's quite a big gap. But do you know how absurdly outdated this is? I don't know why I didn't change it. Because it's the uncertainty in supply that's huge today. So in 2010, there was some uncertainty in demand, and now it's supply, because they've got all that solar in place. And so now, instead of these peaks like that, if you look at last year, I'll show you a plot in the next upcoming lectures. It goes down and then up, and you end up with a 7 gigawatt ramp because of the solar energy in the midday. It's crazy. 7 gigawatt ramp. But what is that, like 5 nuclear generators, one after the other ramping up? Nuclear power generators don't do that. they don't ramp up. You know, it's California's scared to death. You know, completely scared. And that's what's going to make the next lecture sort of fun, because the ISO, meaning the people who control the grid, are scared of the new volatility. And they don't know what to deal with it, and they're coming up with crazy ideas to deal with it. And we're going to be laughing at them all the way. And hopefully laughing to the bank in 5 years. That's what, yep. Yeah.
Tesla recently made batteries.
Yep.
That maybe equal purpose.
Oh, right, yeah. So Tesla's Powerwall is amazing hype, you know. So, you know, I love Elon Musk, and I think he's going to do beautiful things, given his idealism and all that. And I mean, he's a brilliant man, but this is a bunch of hype. I mean, anyone can build batteries, and these are not the best kind. And we're going to have some discussion about that maybe next week, about what the problem is. I mean, and you know, there's very little energy storage in those batteries, and they have a lot of shortcomings. Yeah. And storage. We'll talk about storage. But storage, in some form, will be a big solution to the problems that are being faced. We'll talk about that again in the next lectures. But why on earth do they have such a huge amount of extra capacity than what's needed? Given that their forecast area is so small, why do they keep so much extra? That's something we're going to look at in the next lectures as well. Yeah. And definitely you would need less if you had lots of storage. You know, if you had huge batteries. If everybody had a massive, like maybe a dozen Tesla Powerwalls in their house, you know, it would be a beautiful world. You wouldn't, you know, you'd have to rebuy them every 5 years. But still you could deal with a lot of uncertainty. So what are we committing again? So we don't know precisely supply or demand the next day. And I wish I could get rid of this thing. They've stopped allowing you to do this. So that's why you need reserves. That's what those things are. And so that's something that we haven't been talking about yet. And there's an infinite number of definitions. So the big one that you care about is spinning reserves. These are generators that are not even connected, but they're running. And so you can just, you know, wire them, you know, hook them up, and they can go. And why do you need them? Traditionally, it's because generators go out. So you've got a 400 megawatt generator, wham, it's gone. And you've got to do something quickly to replace that missing energy. And there's a beautiful step-by-step technique to deal with those contingencies. That'll be part of the course. You know, we'll go through explain how it's done today. But that's really a minor concern today. You know, 400 megawatt drop, big deal. We've seen wind gigawatts, you know, drop in an hour. So it's the historical reason for spinning reserves is very different than why we need them today. But then you have all sorts of other things. You have offline, non-spinning resources, quick start generators that may be very expensive. So they might be horrible oil burning generators, but you can get them on fast. And so you bring them in and then you get rid of them as fast as you can. Just, it's temporary relief. And so what California defines here, they explain it on their website. And it's a very complicated mix of spinning and non-spinning reserves. And it's really, again, like I mentioned last lecture, it's crazy, the whole state of California, to talk about total reserves. I mean, if it was all in San Diego, would it help Humboldt County in the north? I mean, it's a transmission grid as well. So this is a very crude, it's an almost meaningless metric. But again, this is to be discussed. But all these things have to come, you have to think about all these issues when you talk about the commitment problem. What resources do I commit the next day? Who's going to be on? And once you know who's going to be on, then you can do the economic dispatch problem that we've been concentrated on the last weeks. So we're going to have to basically define D of t to be something bigger than the forecast. Is what you actually end up doing when you do this. So when we say that the sum of generation is equal to demand, it'll be something beyond your forecast demand to take into account reserves. So it's forecast demand plus reserves. And you can see then how another layer of things falling apart. Again, if the demand wasn't really demand, how can we talk about these welfare functions? It's really strange. I don't understand, how you could do all this theory, economic theory, and then suddenly say, hey, well, we didn't mean D of t anyway, So imagine if we, and so, I've worked on this. You can redo the whole theory, taking into account reserves, and you'll get really similar results. And you'll get average prices, average marginal cost. And what you'll find is the price is normally zero. It'll be the marginal value. And what's the marginal value of extra power if I've already got what I need? Nothing. If I'm a real consumer, reserves are just sitting there doing nothing. I don't care. We could, if we wanted to, redo the whole theory, including reserves. We wouldn't learn a thing. We would just get the same weird results. Okay, so. Again, so other issues, I'll get into some science in a moment, but again, ramp rates, reliability, responsiveness. But startup costs are the biggest thing. The reason unit commitment is so different from the economic dispatch problem is startup costs. Obviously, if I could bring up a generator online instantly at no cost, then I could just do commitment and economic dispatch at the same time. I wouldn't have to separate the two problems, right? But the fact is, it takes maybe hours to get a coal generator. It could take a week to get a coal generator online if it's been out of service for a while. I don't understand why. But coal generators, if they've been out for a week, it can take weeks to get them back online. And I don't know all the reasons for that. But that's the awful, lumpy cost that makes this a combinatorial nightmare. And so, right there, computational nightmare. All right. And let's see if Lagrange multipliers can save us. So I made a joke here, or relax us, So I was at this National Academy of Sciences workshop in February. I've always hated combinatorics. I've got in Texas you've got 500 generators in the ERCOT market, and maybe only 100 of them running. So do you know some combinatorics? 500 choose 100. That's a lot of choices, and it's ugly to me. It scares me and it's ugly. And so a lot of people invested a lot of time in coming up with hacks. Now, it's absolutely impossible to have a general theory for computing the exact optimal solution to that problem. If you know anything about complexity theory, it's infinitely complex. And that's why it's very unsatisfying. Any algorithm you come up with, you can only cross your fingers and hope it works. But it turns out that this problem was a big deal 10 years ago. And there was a workshop held, and they brought in all sorts of people who are experts in optimization, all sorts of areas. And there was one person who was an expert in integer optimization, what's called mixed integer programming. And And nobody believed he could do anything, and then he just went and hacked away, and he showed he could solve their problems in a millisecond compared to their whole day. And it caused a revolution, just absolute revolution. So that's what's done today, is something called mixed integer programming. So MIP, mixed integer programming. So UF is a great place for this. If you want to learn about this, you can take a dozen courses in industrial engineering about how to do this. And I got to meet the guy who actually introduced this to to power markets in the U.S. And the guy's a billionaire. I mean, and just from a bit of code, or hundreds of millions, I don't know. But it's fascinating that you can make such an impact. So we won't go into it again because it's such a specialized thing. It happens to work for this class of problems, and we don't know exactly why. So it's just not the kind of thing that really we can get into. But at least I can say a few things about why the original problem is hard by scribbling on the blackboard. So last night I prepared you all notes. These were handwritten last year. Now they're nicely typed. And I want to do two things. I want to say a few things about Lagrange relaxations that we kind of missed, and then explain how we would try to use our tools in this commitment problem, and how they could work sometimes and could fail in other times. So this guy got lucky. The mixed integer program worked, because of some structure he was able to exploit. Something else might have worked as well, And I can give you the hack I would have tried the first time, which probably, I guess, didn't work. I don't know. All right, so let's turn that off and play with this. So first of all, if any of you want to adapt the course a bit, feel free. So if you feel cheated that I haven't taught you about algorithms, tell me and I will. Okay, I'll even do it outside of lecture. Normally this course, you're given a crash course in all sorts of optimization algorithms, and you're forced to do it. And it's part of the PowerFlow part of the course. And I'd be happy to give a crash course, maybe again outside of class time or something. So in these notes, I won't repeat them, but the two references I've given you before are my favorite. It's a book by Leuenberger, and the other book by Stephen Boyd at Stanford. They're both at Stanford. Is an encyclopedia, which again you've got the reference. Basically, let's go back to, so first there's two things I want to do. Is one, I want to just say something about algorithms. So just last words on all these algorithms we've been talking about, but not mixed integer program again, my convex world where things are more precise. And then I'll say a few things about about unit commitment. But let's just go back to the simplest version of our old friend. Just an optimization problem, the simplest case. Like, it might feel weird to go back to the beginning, but it took you a while to absorb all this material. And there's some big gaps that it's crazy not to know. So this would be like minimizing the sum of the costs of generators subject to supply equals demand, right? But it's much easier just to abstract the problem away. And then we have our dual function. And I keep bragging about the fact that this is concave, and I realize I'm letting you down. And next time I teach this course, maybe I should say this earlier. Why do I claim this? And I said, it's a minimum of linear functions. For each x, that's an affine function of lambda, if you have a collection of affine functions, take their minimum, you get a concave function. That's a fact. But I can make that more precise, okay? And I should have done that at the start. So for one lambda naught, okay, so you all know this picture perfectly now, right? We have, for any lambda, we have eta star. This means no duality gap, right? They actually touch, which is the situation, all these convex problems we're looking at. For the theory to apply, to know there's no duality gap, for equality constraints, remember that's tricky. The only case it works is H is linear to ensure no duality gap. You know, you'd have to have F convex and H linear, you know. You know, it's for inequality constraints, you have much more freedom. H can be convex. Okay. All right, so so if you go back to my definitions of convexity and concavity, this was one of my definitions, is that you could graph the function and find a tangent above the curve at any point. Like when I had a list of definitions of convexity, I had it below. For concavity, it's above. Okay? Now, this turns out to be trivial because of this fact. Let me explain that. So for one lambda naught, let x star naught be the optimizer. Yes. Okay. Now, for any other lambda, this is a minimum over x. If I plug in some arbitrary x, I'll get something maybe bigger. And I forgot the naught. Should have all been screaming. So x star solves dual at lambda naught. Okay? So I have equality there, but I have an inequality everywhere else. Okay, so here you see this is an affine function of lambda, right? A constant plus linear. Affine function of lambda, which touches the graph at one point, and it upper bounds the graph everywhere else. That's what this picture is supposed to signify. Okay, so this line is nothing but that. Let's just call it L of lambda or something.
So something that T star of lambda will.
That this affine function of lambda always sits above the graph.
Oh.
It's just like that. And so that's the definition of concavity, that at any point you can draw a tangent above it. And if there's a corner, all you need is to say there's one tangent. If there's a corner, it could be not unique. If it's unique, it's differentiable. You know. All right. So that's the beautiful fact. That's why you get concavity for free. Okay?
What about the tangents?
What?
The increasing tangent.
Say that again?
The other side. The tangent.
Same thing. You give me give me a lambda 1 here, and I can find another tangent. exactly the same form.
The same form.
Well, exactly the same form. I'll say let x star 1 solve the dual at lambda 1 and blah.
Just
Yeah.
looking for the minimum,
Yeah.
though, right?
What's that? No. This is just, I'm saying the structure. I'm just saying that the dual function has a structure. This shows it's concave. And also, if it's differentiable, what's the derivative? Well, they have the same derivative, right?
Right.
So phi and this little l have the same derivative at this point. And what's the derivative of an affine function? No, lambda is a variable.
Oh, sorry.
Yeah. So
What's each x?
oh, right there, like this would represent supply equals demand, for example.
Oh, okay.
Yeah. So d lambda, I mean. So this equality holds whenever the derivative exists. You know. Yeah. So again, many times there are corners, so it's not unique, you know, but still it's called a subgrade in general. Or subderivative, I'll say. People don't really say subderivative; they say subgradient. But I'll use that language. Even if it's not differentiable, whenever you have this structure, you call this slope of the affine function the subderivative or subgradient. All right.
So why is that true for all lambda though?
All right, right there, min. You know? So this is a min, so I get an upper bound if I stick in some arbitrary x. And the arbitrary x is just that x not star. Because it has no special significance if I choose a different lambda. You know?
Okay.
The whole point is that instead of a min here, I'm just fixing one x. You know? And the only reason I chose it to be optimal is so I get equality at one point. You know, so they'd actually touch. You know, so if I didn't choose x or a star to be optimal, they wouldn't touch there. I could end up with something above. You know.
The thing is, like, isn't that a phi star lambda phi? Wouldn't it be greater than?
Well, this is a min over all x, right? And so if I stick in any old x, I'll get something potentially bigger.
Right, but you said that you're saying phi star is less than
Yeah.
whatever that value is, but shouldn't it be?
Yeah, less than, because it's a minimum. Phi star of lambda is a minimum over all x. So if I stick in some stupid x, I'll get something bigger possibly. Right? Yeah. This minimizes this over all possible x, and that's not. Yeah. Right? So anyway, that's fun. So yep.
As we are increasing lambda naught, so as we increase lambda naught, so hx naught star will decrease.
Well, by concavity,
Yeah.
so the slope does
Yeah, so
decrease.
So at hx naught star equal to 0, the duality is satisfied and we get the.
Yeah. Yeah. Right. Oh, that's yeah. Well, yes. I mean, when. Well, good point. What's the slope of lambda of phi right there?
Isn't it the price?
Forget all that. Just look at this. What's the slope there? 0, right? And so, as pointed out here, if the slope here is 0, then that's 0, and it means we have feasibility. So it's nice. It's a good recap anyway. You know, I think it does. It makes sense to wait a few weeks before saying all this. Yeah. So it shows how once you get optimality, the slope here is 0. It's consistent with feasibility, that h of x 0 star satisfies the constraints that we imposed.
Right?
Well, no, this isn't sensitivity. It's something different. That's the thing. Remember, sensitivity, I had perturbed my constraints. This is a whole different topic. You know, it's a big field. But I need this for algorithms. You know, I'm not torturing you. I mean, you really need this. The most basic algorithms for solving these primal and dual are based on this this structure.
I'm not understanding how you made that relationship of lambda naught of lambda. Like, I don't understand how you explained from. You said
Well, but you,
V star at lambda naught, right, equals a certain.
yeah, well, this was a definition. I mean, suppose that we've solved the problem for a
You're
little.
saying that a V star at any lambda
Yeah.
cannot be greater than.
Well, no, come on. I think you've got too sharp an angle here. So, you know, yeah, because you've only got like 20 degrees. But if I could take this and tilt it, it would be clear, right? I mean, phi star of lambda is defined to be the minimum of all x of this quantity. You know, the minimum. So you must admit that if I put in some arbitrary x, I'll get something bigger.
Right, but wouldn't the highest value be at?
No, minimizing. No, we're not. So we're not trying to optimize phi star right now. I'm just saying. I'm just just giving you upper bound.
But that's not. But how's that the upper bound?
Right there.
Upper bound be at lambda star.
Look. Do you agree that phi star of lambda is the minimum of this over all x? Get rid of the x0 star,
Okay.
right? But so I've just instead of minimizing, I've just plugged in an x0 star, not the best x. You know. I mean, it's yeah. So it's a very, very specific thing. It's not. I'm not talking about trying to optimize it, the dual function or anything. I'm just saying that because phi star of lambda is the minimum of this overall variables, when I plug in some fixed variable, I'll get an upper bound. Yeah. So anyway, that geometry is really important, and it's what's used to try to find this value. You know, because if I'm here, I can look up, and by knowing the slope, I'm trying to maximize. I know I should go that direction. You know, and over here, I'm glad you mentioned lambda 1. If I'm over here and I see the slope there, I'm trying to maximize. I should be going that direction.
So you want to. So if you're at lambda naught, the root of lambda naught is negative, then you know that you have to.
Yeah, go the other direction.
Positive, you know, you have to.
Yeah.
You always want to try to set it to equal to 0 to get that.
In order to get to this point, I want to go with it, yeah. So basically the slope here tells me a direction to go. And the fact that the slope is precisely the constraint violation, that's supposed to be 0, you know, is the basis of algorithms for solving the dual. That's constraint violation, you know. It's supposed to be 0. If it's positive, the constraint violation is one direction. If it's negative, the other. Yeah? All right, cool. So that's how you get to the first basic algorithm. So all these algorithms, you know, you basically write some code, so you initialize with some guess, and then you iterate. You know, so you're always generating. What?
So you set the lambda 1 if it's on the other side, right? If it's less than lambda star, would this inequality still be equal or would it be flipped?
Say that again? If what?
So let's say we're looking at lambda 1, because on the graph you said you assume that lambda 1 was on the other side.
Oh, you know, yeah, it's nothing to do at all. No, it's all based on the fact that this is defined to be a minimum of all x. So it doesn't matter what lambda we choose. You know.
That inequality is true for no matter where, if you have more than one lambda. Like if you have lambda 1 and
Oh God, just maybe think of it another way. You know, suppose x takes real values. If I put in the number 12, I'll have this bound. 12. You know, the thing is that because I've just thrown in a number. You know, I don't need it to be an optimizer anywhere. If I just throw this inequality is true if I throw in any old number here. You know, pi over e. You know, if we're talking x is real value. You know, if x is Rn, I'll take it the vector of zeros. I don't know. Yeah. Yeah. Okay, good. It was worth it, okay? I often need to be slowed down anyway. But so in general, algorithms, they're recursions. The computer scientists get all the credit for and we invent. They write the code, we do the science. It makes us all want to scream. It's true, though. It really is true. I mean, so, I don't know. They talk about taking data and making knowledge and wisdom. Well, we write the code to make wisdom, okay? We write the science for it. But anyway, so mathematicians did this, but not engineers. So steepest descent just says, let's walk uphill. I know. So over here, the slope is positive, means I want to go that direction. I want to increase. And over here, the slope is negative, so I want to go that way. I want to decrease. And so this would be this, but we don't even know if the derivative exists. But we know that even if there was a corner there, this would be the right direction. Even if there was no derivative, the slope of the linear function gives us the right direction. So forget that. We can just say just take it to be that. Now, of course, that involves computing the solution to an optimization problem. So in order to do one iteration for this dual, you have to do one iteration for something like the primal, And that's why, because of this is called a primal dual method. Because we don't have a closed form expression for this function. We can't just go and differentiate this thing because we don't even know what it is. So instead, we actually have to solve and find that optimizer in the nth stage. So to start things off, we get an initial condition. We get it. We find the optimizer here, and then that gives us this initial slope S0 and gets things going.
So we had to solve that equation.
Over and over again. So these things are complex, and luckily code. You all are lucky. Like when I was a grad student, man, punch cards were just made obsolete. It would have taken It would taken hours to do one run, and now it's a millisecond. So But you didn't ask me about gamma. Obviously, gamma is not negative because you want to go the right direction. But gamma is positive. So it can be anything, but if you make it too big, it's not going to work. Because what can happen is you can start here, and you go, whoa! And then you go, whoa! And then, whoa! And you can oscillate back and forth to infinity. It's a gain. It's a gain. Gain. It's a gain of the algorithm. Because it's like a differential equation. Lambda dot equals a gain times the slope. And if you make it too small, then you'll curl along. But if you start locally and things are nice and convex here, if you start nearby, it'll always converge, regardless of the gain. As long as you have some strong convexity here. If it's really a corner, then it's a little more subtle. You can really end up jumping around. I mean, it can really be, it can be nasty. In fact, if there's a corner, you can just oscillate forever really easily and not converge. All right, so that's the basic algorithm. Oh my God, and there's 7 minutes left. Shit. And I don't want to say anything much more about unit commitment. Questions? It's your fault. No, but okay. So anyway, so this is the most basic algorithm, and Lambda is going to be a vector in general, and then gamma will be a matrix gain. And choosing that matrix gain, there's a whole science for that, which you take a course, take an optimization course, okay? Because remember, I was talking about one constraint, but in the problems we've looked at, there are a lot of constraints, and so lambda is a big vector. But the form of the algorithm doesn't change at all. And so that's why I say it's usually called a subgradient, because nobody cares about one-dimensional problems. Lambda is 100 dimensions or something. All right.
So
Yeah.
what you do is you just like find like multiple lambdas until you.
No, well, the thing is that you run this until you think you've converged well enough.
Oh, okay.
And so, yeah, that's a good question. So what's the criterion to stop? I mean, you can go and you can look at your slope, and when that's close enough tolerance, you say, I'm done. And you maybe this is, instead of being 0, is 10 to the minus 5. Well, you just tweak it a bit and make it 0, make it feasible. Eventually you have to stop. So none of these algorithms are meant to stop in finite time, except for linear programs. Linear programs are the only things that, and that's, you exploit the fact there's a corner, and you get to the right answer in finite time. Okay. Yeah. But if it's quite, if it's
h of x of n star is 0.
then you're done.
Yeah.
Then we know we're done.
Right, the lambda naught is
Yeah. As soon as we're feasible, we're done. As soon as this thing wants to stop, the slope is 0. Presto, you've optimized. Yeah. Yeah. That's right. Because that means that you've got a roof. You can see the geometry beautifully. That if the slope on top is 0, I mean, it's better than calculus, because even if, well, never mind. But I have a proposition. You all read this. It's too boring to go through anyway. I'll ask you about it on next lecture. It's just, I don't want to. Because our friends are about to storm in a few minutes, right? But so we won't do this, but it would be better for you all to think about it anyway. So so you have this. Again, I don't think I want to spend a half an hour doing this next time in lecture. This was much more important. I'll think it over, but you think it over too. If I've got 500 generators and want to decide which of 100 I want to be running, and which to be running at each hour of the day the next day. So I've got 500 generators in 24 hours. That's a lot of decisions, you can introduce indicator variables. So I mentioned these in these notes. So, so before our only variables were generation. We had gi of t was the power level of generator I at time t. If we wanted to do the commitment problem, one approach, which was used, was to just put in binary variables. That's why it's a mixed integer program, because one of your variables now is integer. ui of t is 0 or 1. And it's subject to some very strange costs, because there's startup cost and shutdown